Okay, we've seen that the vector -3, 4, 2 can be represented in three-dimensional space by a vector that goes on a diagonal of this 4 by, well, -3 by 4 by 2 box in three-dimensional space. I want to say a little bit more about this, analogous to what I've done here. I can draw a right triangle. I can go from here to here in the xy plane, from the origin to the point -3, 4, 0, and then from the point -3, 4, 0 up to the point -3, 4, 2 straight up. Since the z-axis is perpendicular to both x and y, therefore perpendicular to the xy plane, this segment is perpendicular to this one. So we have a right angle here. Now we can bring this purple triangle out here. Let's turn it around where we can look at it face to face. So here it is. The length of this side, by the Pythagorean theorem, is the hypotenuse of a triangle that's 4 units this way and 3 units this way. So that this has length. Well, let's write it down here. The square root of 3 squared plus 4 squared. Now that turns out to be the square root of 5, but we're not going to worry about that. Okay? The length of this side then is the square root of 3 squared plus 4 squared. The length of this side, well, this is the side that corresponds over here. It clearly has a length of 2. So let's see. Okay, this side has this length. Should be clear that this side has length 2, since how do we get from -340 to -342 by moving up 2 units? So this has length 2. So the length of the hypotenuse is the square root of the square of this I didn't quite have room to write that out. Gonna mess with my picture a little bit. Okay. Now hopefully that's legible. It's the square of square root of 3 squared plus 4 squared. In other words, the square of this plus the square of this, which is just 2 squared. And I can write out that result a little easier to write legibly with the white chalk. Okay, I can't see. Okay, there I am. Okay, it's the square of this plus the square of this. And that equals, well, if you square the square root of 3 squared plus 4 squared, you get 3 squared plus 4 squared. And then here you get your 2 squared. And what we've shown, and I hope that it's legible, yeah, it's readable there. Not always sure where the camera's focused, apologies for that. And there's some writing on the screen of that I'm looking at, and I can't tell that we can see this. Okay, but there it is. Okay, the conclusion is that if I have the vector that I'll rewrite here, and the vector is -3, 4, 2, that we can generalize the Pythagorean theorem. Okay, Pythagorean theorem here, if we got 5, 3, the length has magnitude 5 squared plus 3 squared. If we have -3, 4, 2, the result, the length of the vector is 3 squared plus 4 squared plus 2 squared. Now really, technically, we should probably have the -3 quantity squared, but since we're squaring these, negative signs always square out to positives, so we have this. Okay, so we can actually conclude then that the length of the vector and let's just say we want to represent it by x, y, z. It's the square root of x squared plus y squared plus z squared. This simply extends what we get for a vector in 2 dimensions. We then can extend this to higher dimensions. If we want to talk about a column vector with 5 numbers. Okay, now that's in 5-dimensional Euclidean space. We can do a lot with 5-dimensional Euclidean space, but one thing we certainly can't do is visualize it. We can visualize only up to 3 dimensions because we live in 3 dimensions. At least our perceptions are all in 3 dimensions, and that's as much as I want to say about that. Okay. So if we have 5 of these, we might list them as x1, x2, x3, x4, x5, and the magnitude or length of that vector would be x1 squared plus x2 squared plus x3 squared plus x4 squared plus x5 squared. Okay. Whatever number of rows we have in this column vector, because of course you have row 1, row 2, row 3, but only one column. We're going to square that many numbers and take the square root. That's going to give us the length or magnitude of that vector.